Right now, the light reaching your eyes from the nearest star beyond our sun has been traveling for 4 years, 3 months, and approximately 22 days. That is the closest star, the nearest neighbor in a universe that contains an estimated 2 trillion galaxies. 4 years for the closest one. And yet, when you look up at the night sky, it feels immediate. It feels present. The stars seem to hang there just above you, as if you could reach out and disturb them. But you are not seeing the sky as it is. You are seeing it as it was. Every point of light above you is a message from the past, arriving now, only now after a journey so long that the civilization that launched, no ship built, no transmitter, sent no signal, could possibly have imagined the distance it would cross. This is where we begin. Not with a telescope, not with an equation, but with a simple and quietly devastating truth. When you look into the night sky, you are looking into time. The light from a star, 10 light-years away, left its source a decade ago. The light from a galaxy, 2 billion light-years away, began its journey 2 billion years before you were born, before your parents were born, before the first human being ever stood upright on this planet and turned its face toward the stars. That galaxy may look sharp and present in a long exposure photograph, but what you are seeing is a ghost, a record, an image of something that existed 2 billion years ago, preserved in photons that have crossed the universe to land finally in your eye or on a detector, or in the data of some satellite drifting silently above the atmosphere. That is what the night sky actually is. Not a ceiling, not a backdrop, a window into the deep past of the cosmos, a layered archive of light that left its sources at different moments in cosmic history and arrives here simultaneously all at once, as if time had been folded and pressed flat against the darkness. Above you. But here is what most people, even most people who think carefully about space, consistently underestimate. The light we can see represents only a fraction of what exists, an almost incomprehensibly small fraction. There is a boundary beyond which no light has had time to reach us, not because the universe ends there, not because space stops, but because the universe has only existed for a finite amount of time, and light, for all its extraordinary speed, cannot cross an infinite distance in a finite duration. That boundary has a name. We call it the edge of the observable universe, and it sits approximately 46 billion light-years away in every direction, not 13.8 billion. 46 billion. The difference matters, and we will return to it. But first, sit with the number itself. 46 billion light-years in every direction. If you shrank the entire observable universe down to the size of the Earth, a single light-year would be smaller than a red blood cell. The distance from the Earth to the Moon in this model would be a length you could not see with any microscope currently in existence. Everything you have ever known, every mountain, every ocean, every city, every person, every moment of recorded human history, would occupy a space so small in this model that it would be, for all practical purposes, nothing. And that is only what we can see. Beyond the edge of the observable universe, space continues. We have every reason to believe it continues. The physics does not change at the horizon. The laws of nature do not collapse beyond that line. There is no wall, no membrane, no place where the cosmos simply stops and something else begins. The observable universe is not the universe. It is our universe, the portion we have access to. The region from which light has had enough time to reach us, given that the universe has only been in existence for 13.8 billion years. Everything beyond that boundary exists in a kind of permanent silence, not because it is empty or dark or absent, but because no signal from those regions has ever arrived here. And depending on how space is behaving, some signals never will. This is the question we are going to follow tonight. Not just how far the observable universe extends, not just what lies at its edge, but what it means to live inside a bubble of visibility in a cosmos that almost certainly extends far beyond it. What it means to be surrounded in every direction by a darkness that is not empty, but simply unreachable. What it means to build an entire science, an entire understanding of reality from light, that represents only the nearest, most recent, most accessible fraction of everything that exists. If you find that these kinds of journeys, the slow and careful kind, the ones that leave you staring at the ceiling long after they end, are something you want more of, I would be grateful if you took a moment to give this video a like and to subscribe to this channel. It costs nothing and it means a great deal. Every signal helps this kind of work reach the people who need it most. Now, make yourself comfortable. Let your body settle. Let the room be quiet around you. Let's begin. The first thing to understand is the nature of the horizon itself. We use the word horizon in a very specific way in cosmology. It does not mean a physical edge. It does not mean a place you could travel to and then stand at the boundary and look outward into nothing. The cosmological horizon is defined entirely by light and time. It is the distance beyond which light has not had enough time to reach us since the moment the universe became transparent to radiation. That moment occurred approximately 380,000 years after the Big Bang. Before that point, the universe was filled with a dense hot plasma, a soup of particles so tightly packed and so violently energetic that photons, the fundamental particles of light, could not travel more than a tiny distance before colliding with an electron and scattering in a new direction. The universe in those early moments was opaque. If you could somehow have been present in that early cosmos, you would not have been able to see anything. Not darkness, exactly, more like the interior of a star, bright, hot, impenetrable. Then, as the universe expanded and cooled, something changed. Electrons slowed. Protons and electrons began to combine into the first neutral atoms, mostly hydrogen, some helium. And as those atoms formed, the universe became transparent almost overnight in cosmic terms. Photons that had been trapped for hundreds of thousands of years were suddenly free to travel. They streamed outward in all directions, filling the universe with light for the first time. That light is still traveling. Right now, as you lie here, that ancient radiation is moving through this room. It has been stretched by the expansion of space from its original high-energy wavelengths into the microwave range. It is cold now, only about 2.7 Kelvin, just a fraction above the coldest temperature that physics allows. But it is present. It is everywhere. We call it the cosmic microwave background, and it represents the farthest back in time we can ever see using light. Everything before that moment, the first 380,000 years of the universe's existence, is hidden behind what cosmologists sometimes call the surface of last scattering. It is not that nothing was happening during those early years. Extraordinary things were happening. The universe was forming its first structures, laying down the seeds of everything that would come, but we cannot see it directly. The light from that era never escaped. It was absorbed before it could travel. The cosmic microwave background is therefore not just the oldest light we can detect. It is the oldest light that exists in any detectable form. It is a snapshot of the universe at the moment it first became readable. And when we map that ancient light, when we point sensitive satellites in every direction and record the faint temperature variations written across the entire sky, we find something remarkable. Uniformity, not perfect uniformity. There are tiny variations, fluctuations of about 1 part in 100,000 subtle differences in temperature and density scattered across the background. But the overall picture is almost perfectly smooth. No matter where we look, the background is essentially the same temperature, the same density, the same ancient glow. This uniformity is not something we would necessarily expect. It requires an explanation. And that explanation leads us to one of the strangest and most consequential ideas in all of modern cosmology. But we are getting ahead of ourselves. For now, hold this single image. A sphere of light, 46 billion light-years in radius, centered on the point in space where you currently exist. Not because you are special, not because this location is the center of the universe, but because you are the observer. Because this is your light cone, your window, your horizon. Inside that sphere, we have maps. We have data. We have hundreds of billions of galaxies catalogued and studied and photographed. We have the detailed temperature map of the background radiation. We have a remarkably complete picture of how matter has arranged itself across cosmic time. Outside that sphere, we have nothing, not emptiness, space. More space almost certainly filled with more galaxies, more stars, more of the cosmic web of structure we see on our side of the line. But no signals, no information, no light, just distance. And that distance is not shrinking. Because the universe is expanding, And because the rate of that expansion has been increasing for billions of years, driven by a force we do not yet understand, many of the regions beyond our current horizon are moving away from us faster than light can travel across the gap. Even if we waited, even if civilizations far more advanced than ours pointed instruments of unimaginable sensitivity at the sky billions of years from now, those regions would never appear. The light they emit today is already losing ground, already falling behind, already destined to travel forever through expanding space without ever closing the distance to us. They exist. We are simply not connected to them. That is the horizon of light, not a wall, not an ending, a limit of connection, the boundary beyond which the universe becomes permanently silent, not because it has nothing to say, but because the space between us is growing faster than any message can cross it. And from here, everything else follows. 0, 8, 3, 1. Claude responded. It is a question that sounds almost childlike the first time you hear it. It is a question that sounds almost childlike the first time you hear it. Is the universe infinite? And yet the longer you sit with it, the heavier it becomes. Because it is not really a question about size. It is a question about the nature of reality itself, about whether existence has limits, about whether the word everything actually means everything, or whether it means something smaller, something local, something that only feels like everything because we cannot see past its edges. When scientists use the word infinite, they do not mean very large. They do not mean larger than we can imagine, though. That is also true. They mean without boundary, without end. A space in which you could travel in a perfectly straight line for 1 trillion years and still not find a wall, a border, a place where space simply ceased to be. Not a space that is big enough to seem endless. A space that is actually endless. That is a different kind of thing. And the honest answer is that we do not know whether our universe is that kind of thing. What we know is this. The observable universe has a diameter of approximately 93 billion light-years. That is the sphere of space from which light has had time to reach us. It is vast beyond any ordinary conception of vastness. If you tried to count every star in the observable universe at a rate of 1 per second, you would need roughly 100,000 times the current age of the universe to finish. You would be counting long after every star had burned out, long after the last black hole had evaporated, long after every structure in the cosmos had dissolved into a thin, cold haze, and that is only what we can see. Beyond the edge of our observable sphere, space continues. The physics does not change at the horizon. There is no reason to expect the universe to suddenly become different or empty or absent just because we cannot receive signals from it. The most natural assumption, and the one supported by everything we observe, is that the universe extends far beyond our window. Perhaps enormously far, perhaps without limit. But enormously far and without limit are not the same thing. To understand the difference, you need to think about geometry. Not the geometry of shapes on a page, but the geometry of space itself. The shape of the universe. Because the universe has a shape, even if that shape is not something you can see from the outside, there being no outside to see it from, there are 3 broad possibilities. The first is a flat universe. In a flat universe, space obeys the familiar rules of classical geometry. Parallel lines stay parallel forever. The angles of a triangle add up to exactly 180 degrees. If you travel in a perfectly straight line, you never return to your starting point. Space simply continues in all directions without curving back on itself. A flat universe can be infinite. It does not have to be, but it can be. And if it is flat and does not loop back on itself in some subtle topological way, then it almost certainly is infinite. The second possibility is a closed universe. A closed universe is one that curves in on itself like the surface of a sphere, but extended into 3 dimensions. In a closed universe, if you travel far enough in any direction, you eventually return to where you started. Not because you turned around, not because there is a wall, but because space itself curves back. A closed universe is finite in volume. There is only so much of it, but it has no edge. You could search every part of it and never find a boundary. It is finite but unbounded, the way the surface of the Earth is finite but has no edge. The third possibility is an open universe. An open universe curves in the opposite direction like an infinite saddle. Parallel lines diverge. Triangles have angles that add up to less than 180 degrees. Space goes on forever, but in a way that is subtly different from flat space, expanding outward in geometry as well as in content. Which of these describes the universe we actually live in? The answer, based on the most precise measurements we have ever made, is the first one: flat, almost perfectly flat. The evidence comes primarily from the cosmic microwave background. When scientists map the tiny temperature fluctuations in that ancient light, those fluctuations appear at certain characteristic angular sizes in the sky. If the universe were closed, those features would appear slightly larger than expected because the light paths would curve inward. If the universe were open, they would appear slightly smaller. But what we see matches the predictions of a flat. The universe is flat to within a margin of about 0.5%, not exactly flat perhaps, but so close to flat that any curvature, if it exists, is below our current ability to detect. This has an enormous implication. A flat universe, if it does not loop back on itself, is almost certainly infinite, not probably very large, not effectively unlimited, genuinely actually infinite. A space with no end, no repetition, no final boundary, stretching outward forever, in all directions. And here is where the idea begins to press against something in the mind. Because an infinite universe does not just mean a very large number of galaxies. It means an infinite number, not a number so large we cannot count it, an actual infinite number. And if the universe is infinite, and if matter is distributed across it in roughly the same way it is distributed in our observable region, then every possible configuration of matter that the laws of physics allow will not only occur somewhere, it will occur an infinite number of times. Somewhere in an infinite universe, there is a planet exactly like this one, not approximately like this one, exactly like this one. With the same oceans, the same continents, the same cities, the same night sky, the same person lying in the same room listening to the same voice, describe the same incomprehensible vastness. Not because the universe is designed to repeat, but because in an infinite space, probability does not have the option of saying never. It can only say, not here, not yet. That conclusion makes some people deeply uncomfortable. It makes others feel oddly at peace. But it does not require any new physics. It requires only that the universe be genuinely infinite and that it be roughly uniform on large scales, both of which are consistent with everything we currently observe. There is, however, an important qualification. We cannot actually confirm that the universe is infinite. We can only measure the part we can see, and within that part, space appears flat. But flat does not absolutely require infinite. A universe could be flat and still have a finite volume if its topology, the way it connects to itself, causes it to loop back. Imagine a three-dimensional version of a video game screen where objects that pass through the right edge reappear on the left. The space would be flat in the geometric sense but finite in volume. No edge, no wall, just a space that wraps. If the universe has that kind of topology, we might be able to detect it. We would look for repeated patterns in the cosmic microwave background places in the sky, where the same structures appear in multiple directions as if we were seeing the same region from different angles. Searches for this signature have been conducted. So far, nothing has been found. If the universe does wrap back on itself, it does so on scales much larger than our observable sphere, so large that the repetition, if it exists, is beyond our reach. Which brings us back to a thought that will return several times throughout this journey. The observable universe may be a small patch of something far larger, and far larger may mean infinite, or it may mean so enormous that the distinction between infinite and nearly infinite has no practical meaning for anything we will ever observe or measure or understand. Now let us go one level deeper, because the question of how far the universe extends is not only a question about what exists now, it is also a question about what happened at the very beginning, about the first fraction of the first second, about a process so extreme, so fast, so far outside any ordinary conception of change that it altered the structure of space permanently and on the largest possible scales. That process is called inflation. In the first moments after the Big Bang, before any stars formed, before any atoms existed, before the universe had cooled enough for light to travel freely, space is believed to have undergone a period of extraordinarily rapid expansion, not the slow, steady expansion we observe today, not even the faster expansion of the early universe. Something categorically different, an expansion so violent and so swift that the observable universe, all 93 billion light-years of it, inflated from a region smaller than a proton in a time so brief it makes a nanosecond seem like an eternity. We're talking about a doubling of the size of the universe roughly every 10 to the negative 37 seconds. An expansion faster than the speed of light, which is permitted when it is space itself that is expanding rather than objects moving through space. In a fraction of a second that contains more zeros after the decimal point than there are atoms in the observable universe space, stretched from the unimaginably small to the cosmically vast. Why do we believe this happened? Because of the uniformity problem. The cosmic microwave background is almost perfectly uniform in every direction. The temperature of that ancient light is the same to 1 part in 100,000, whether you measure it here or there, north or south, in any direction across the entire sky. But if the early universe expanded slowly, regions of space on opposite sides of the observable universe should never have been in contact with each other. They should never have had time to exchange energy, to equilibrate, to reach the same temperature. They should look different. But they do not. Inflation solves this by saying that the entire observable universe inflated from a single tiny region that was already in thermal equilibrium. Everything we can see was once in contact, once mixed, once uniform. Then inflation stretched that small balanced region into something enormous. The uniformity we see today is the uniformity of that original tiny patch stretched across the sky. But inflation does something else. Something that makes the question of the universe's size even more extraordinary. If inflation happened in our region, if space in our patch underwent that violent and rapid expansion, there is no reason to assume it only happened here. The field that drove inflation, the mechanism that caused space to expand so rapidly, may have behaved differently in different regions. Some regions may have stopped inflating early like ours. Others may still be inflating now, expanding faster than light, driving space apart at rates no signal could ever cross, creating vast regions of the cosmos that will never intersect with ours, not now, not ever, not in any possible future. This leads to a picture of the universe that is almost beyond conception, not a single universe that inflated once and then settled, but an endlessly inflating space in which pockets of normal expansion regions like ours continually form and evolve and grow, each one becoming its own observable universe to whatever observers might exist within it, each one separated from all the others by a growing ocean of still inflating space. Our observable universe, our 46 billion light-year sphere, our 2 trillion galaxies, a single bubble in a sea of bubbles that may never stop forming. Whether that sea is truly infinite, whether it stretches without end in some higher dimensional sense, we do not know, but it is almost certainly far larger than anything we can see or reach or measure. And the question of how far it goes is one that may never have an answer accessible to us. Not because we lack the intelligence to find it, but because the physics of space itself places that answer permanently beyond the reach of any signal we could ever send or receive. How far is forever? Far enough that the question itself may be unanswerable from where we stand, and yet we keep asking. That is the thing, we keep asking. 0833, Claude responded. There is a number that governs everything you will ever see, everything you will ever know, everything that can ever reach you from across the cosmos. There is a number that governs everything you will ever see, everything you will ever know, everything that can ever reach you from across the cosmos. It is not a large number, not by cosmic standards. It is approximately 299,792 kilometers per second, or if you prefer the older unit, roughly 186,000 miles per second. That is the speed of light. And it is not merely the speed at which light happens to travel. It is the maximum speed at which any information, any signal, any effect, any consequence of any event anywhere in the universe can propagate. It is not a record waiting to be broken. It is not a technological barrier that a sufficiently advanced civilization might one day overcome. It is a structural feature of reality itself, woven into the fabric of space-time at a level so fundamental that to exceed it would not merely require extraordinary engineering. It would require the universe to be a different kind of thing than it is. Nothing moves faster than light, not because we have not tried, not because we have not imagined it, but because the mathematics and the physics and every observation ever made all converge on the same conclusion. The speed of light is the speed limit of causality. The fastest that cause can reach effect, the fastest that one event can influence another, the fastest that the universe can communicate with itself. And because of that single fact, the night sky is not what it appears to be. When you look up at the stars, you are not seeing the universe as it is. You are seeing the universe as it was at different moments in the past, all compressed into a single present moment of observation. The star 4 light-years away appears to you as it was 4 years ago. The star 400 light-years away shows you a scene from 4 centuries past. The galaxy 2 million light-years away is presenting you with an image from a time before our species existed, before any of our ancestors had discovered fire, before the most recent ice age had ended. You are not looking across space. You are looking back through time. And the deeper you look, the further back you go. The most distant galaxies visible to our best telescopes show us the universe as it was more than 13 billion years ago. We are not seeing those galaxies as they are now. We are seeing them as they were when the universe was only a few 100 million years old, when the first structures were still forming, when the cosmos was young, in a way that has no analogy in ordinary human experience. Those galaxies look small and faint and primitive in our images, but they were not primitive. They were the seeds of everything. And between the moment their light left them and the moment that light arrived in our instruments, entire civilizations could have risen and fallen on the planets circling their stars. Stars could have been born, burned for billions of years and died. The galaxies themselves could have merged, transformed, evolved beyond recognition. We would not know. The news has not arrived yet. This is one of the strangest and most quietly unsettling aspects of living in a universe governed by a finite speed of light. We are always receiving delayed information, always working from old data. The universe we observe is not the universe that exists. It is a layered record of the universe that existed at different moments across different distances, all received simultaneously, as if time were a dimension we could look across the way we look across a landscape. But the speed of light does something even more consequential than create this temporal parallax. It creates a hard boundary around every event in the universe, a limit to how far any influence can spread. Imagine a single event, a star exploding, a signal transmitted, a stone dropped into water. That event sends out effects in every direction at the speed of light or slower. Those effects travel outward, forming an expanding sphere. And everything inside that expanding sphere, everything that the effects can reach in a given time, is what physicists call the future light cone of the event. Everything outside that sphere, everything the effects cannot yet reach, is causally disconnected from the event. It has not been touched. It does not yet know the event occurred. The same geometry works in reverse. Every observer, including you, has a past light cone, a region of space-time from which signals could have reached your current position at the speed of light or slower. Everything inside your past light cone is in principle something you could have received information about. Everything outside it is in principle something that could not have influenced you. The edge of the observable universe is the edge of your past light cone, extended back to the beginning of cosmic time. It is not a physical boundary. You could in principle pass through it and keep traveling. But as you crossed it, you would not be entering a region of empty space. You would be entering a region from which no information has reached the point you started from. A region whose history has been inaccessible to your origin point. A region that exists in the universe but not in the observable universe of the place you left. This might seem like a technicality, but it has profound consequences. Because space is expanding, and because the rate of that expansion is accelerating, there are regions of the universe from which light is losing ground as we speak, not slowing down. Light always travels at the same speed through local space. But the space it is traveling through is stretching. For every meter of progress a photon makes toward us, space adds more distance to the gap. If the space adds distance faster than the photon can cover it, the photon never arrives. That is already happening, right now, for a significant fraction of the universe. There is a distance called the Hubble radius, beyond which galaxies are receding from us faster than light can travel across the expanding space between us. Galaxies beyond that distance are not moving through space at superluminal speeds. Space itself is expanding at a rate that creates an effective recession velocity exceeding the speed of light. And light from those galaxies, light that left them long ago and has been traveling toward us ever since, is currently losing the race, moving in our direction but falling behind, adding distance faster than it can close it. Some of that light will eventually reach us. The Hubble radius is not fixed. It shifts as the expansion rate changes. And some photons that are currently losing ground will eventually find themselves in a region of space that is expanding more slowly, allowing them to make progress and eventually arrive. But others will not. There is a boundary farther out than the Hubble radius, called the cosmic event horizon. Beyond that boundary, light emitted today will never reach us, not in a billion years, not in a trillion, not in any finite amount of time. The space between us and those regions will expand without end, carrying those photons further and further from arrival with every passing moment. Those regions are not inaccessible because of our limitations. They are inaccessible because of the structure of the universe, because dark energy is driving expansion to accelerate, because the gap is widening faster than causality can bridge it. Those galaxies, whatever they contain, whatever happens within them, are permanently beyond our horizon. Their future light will never reach us. We will never know what they become. Think about what that means for a moment. Truly let it settle. There are stars in those galaxies. Almost certainly, there may be planets. There may be, for all we know, observers. Beings who have looked up at their own sky and asked their own version of this same question. Beings whose light, whose radio signals, whose every transmission into the cosmos is traveling toward us right now and will never arrive. Not because the signal is too weak, not because we lack the instruments to receive it, but because the universe itself is expanding the distance between us faster than any message can cross it. We are separated not by space, but by the behavior of space. And there is something even stranger embedded in this picture. Because we are not special in this regard, we are not at a unique location. Every observer in the universe, wherever they are, faces the same situation. Their observable universe is centered on them. Their cosmic event horizon surrounds them. There are regions beyond their reach, just as there are regions beyond ours. And some of those regions are within our observable universe. Observers far from us can see things we cannot. Their past light cone extends in a different direction, overlapping with ours in some areas but not others. If there is a civilization on a planet near one of the most distant galaxies we can observe, their observable universe includes our region but barely. We sit near the edge of their sky, our light just barely arriving after its 13 billion-year journey. And from their perspective, we are the primitive, distant, barely visible galaxy at the edge of their window, showing them an image of our region from billions of years ago. We are their past. They are ours. And neither of us can know what the other looks like now. The speed of light is the reason for all of this. Not a fast speed, but a finite one. Not arbitrary, but fundamental. It sets the pace of causality, the size of the observable universe, the boundary between connection and isolation. It determines what you can know and what you cannot, what has reached you and what never will. It is the most important number in cosmology, not because of what it allows, but because of what it prevents. Because it prevents the universe from being fully known from any single point within it. Because it guarantees that every observer is surrounded by a horizon they cannot see past. Because it means that the cosmos, however vast, however rich, however full of structure and complexity, and perhaps even consciousness, will always present itself in fragments, pieces arriving at different times from different distances, a picture assembled slowly, incompletely, from light that has been traveling since before any of us existed. The speed of light does not limit our ambition. It does not limit our curiosity. It does not prevent us from asking what lies beyond our horizon. It only ensures that the answer, whatever it is, will never come to us directly. We will have to infer it. We will have to reason toward it. We will have to build models from what we can see and extend those models carefully into the dark. That is what we have been doing for centuries. And that careful extension, that slow and patient reaching beyond the edge of what is visible, is exactly where we are headed next. 0835. Claude responded. There is a temptation when thinking about the expanding universe to picture it the way you might picture an explosion. There is a temptation when thinking about the expanding universe to picture it the way you might picture an explosion. A single point, a violent release of energy. Matter flying outward in all directions through pre-existing space, the way shrapnel flies from a detonation, the way sparks scatter from a fire. The Big Bang as a kind of cosmic explosion, sending the contents of the universe racing away from a central point into the emptiness that surrounds it. That picture is wrong. Not approximately wrong, not wrong in its details, while correct in its broad outline. Fundamentally, structurally completely wrong in a way that matters enormously for understanding what the universe actually is and how it actually behaves. The universe did not explode into space. Space itself expanded. There was no pre-existing void into which matter was launched. There was no central point from which everything fled. There was no outside. Space-time, matter, energy, the entire contents and container of reality, all of it came into being together. And what has been happening ever since is not that things are moving through space away from a center. It is that space itself is growing. The distances between things are increasing, not because things are moving, but because the medium they occupy is stretching. This is not a semantic distinction. It changes everything about how we interpret what we observe. The first person to measure this stretching with precision was a man named Edwin Hubble, working at the Mount Wilson Observatory in California in the late 1920s. Hubble had been cataloging distant objects in the sky, objects then called nebulae, some of which he had recently confirmed were not clouds of gas within our own galaxy, but entire separate galaxies, island universes of billions of stars separated from the Milky Way by distances so vast they had barely been conceived of before his work. What Hubble noticed, and what transformed cosmology permanently, was that the light from these distant galaxies was shifted, not randomly, not in different directions for different galaxies, systematically, consistently in one direction. The light was redder than it should have been, shifted toward the longer wavelengths of the spectrum, and the further away the galaxy, the greater the shift. This is what we call redshift, and in the context of an expanding universe, it has a precise physical meaning. When space expands, the wavelengths of light traveling through that space expand with it. A photon that begins its journey with a certain wavelength, a certain color, a certain energy arrives at its destination with a longer wavelength, a redder color, a lower energy, not because anything happened to the photon directly, not because it lost energy to friction or resistance, but because the space it was traveling through stretched while it was in transit, and the photon stretched with it. The amount of stretching tells you how much space expanded during the photon's journey. The more redshifted the light, the more the universe has expanded since that light was emitted. It is a direct measurement of cosmic expansion written in the color of ancient starlight. Hubble's observations showed that galaxies were receding from us, and that the recession velocity was proportional to distance. Twice as far meant twice as fast. 3 times as far meant 3 times as fast. This relationship, now called Hubble's law, is a direct consequence of uniform expansion. In a uniformly expanding space, every point moves away from every other point, Jaffa, at a rate proportional to the distance between them. There is no center, there is no preferred location. Every galaxy sees every other galaxy receding, and every observer, wherever they are in the cosmos, sees the same pattern. Think of dots drawn on the surface of a balloon. As the balloon inflates, every dot moves away from every other dot. No single dot is the center of the expansion. No dot is standing still while the others flee. The surface itself is growing, and every dot participates equally in that growth. That is the universe. And like the balloon, the expansion carries no implication of a center, no implication of an edge, no implication that things are moving through space in the conventional sense. Space itself is the thing that is changing. The distances are increasing because the medium is stretching, not because its contents are in motion relative to some fixed background. For decades after Hubble's discovery, cosmologists assumed that this expansion was slowing down. The reasoning seemed sound. Gravity is universal. Every particle of matter in the universe exerts a gravitational attraction on every other particle. The universe is full of matter. Therefore, the universe's expansion should be gradually decelerating, the way a ball thrown upward decelerates as gravity pulls it back. Perhaps the universe would eventually stop expanding and begin to collapse. Perhaps it would expand forever, but at an ever-decreasing rate. Either way, the expectation was deceleration. In 1998, that expectation was shattered. Two independent research teams, the Supernova Cosmology Project and the High-Z Supernova Search Team, were using a particular type of exploding star, a type Ia supernova, as a measuring tool. These explosions are extraordinarily useful in cosmology because they all occur with approximately the same intrinsic brightness, like standard candles placed at different distances. By measuring how bright they appear in the sky and comparing that to how bright they should be, you can calculate how far away they are with considerable precision. What both teams found independently using different supernovae in different parts of the sky was that the most distant explosions were fainter than expected. Not slightly fainter. Fainter in a way that could only be explained if they were further away than a decelerating universe would predict. The universe was not slowing down. It was speeding up. The expansion of space was accelerating. Distances were not increasing at a constant rate or a decreasing rate. They were increasing faster and faster, driven by something that was not matter, not radiation, not anything that had been accounted for in the standard models of cosmology at the time. That something was given a name: dark energy. The name tells you almost nothing about what it actually is. That is intentional, or at least honest. We do not know what dark energy is. We know what it does. We can measure its effects with remarkable precision, but its fundamental nature remains one of the deepest unsolved problems in all of physics. What we know is this: dark energy is not a substance in the ordinary sense. It does not clump. It does not form structures. It does not interact with matter in any way we can detect directly. It appears to be a property of space itself, a kind of energy density inherent to the vacuum, present everywhere uniformly and crucially not diluting as space expands. As the volume of the universe increases, the total amount of dark energy increases proportionally. There is simply more of it as space grows because it is a property of space rather than something contained within space. This behavior is what makes it so strange. Every other form of energy in the universe dilutes as space expands. Matter becomes less dense. Radiation becomes less dense, and also redshifts, losing energy. But dark energy maintains its density. And because it maintains its density, while the universe grows, it comes to dominate the energy budget of the cosmos over time. In the very early universe, matter and radiation dominated. Dark energy was present, but negligible. Gravity held sway, and the expansion, while still happening, was indeed decelerating. But as the universe expanded and matter thinned out, dark energy became relatively more important. Roughly 5 billion years ago, it crossed a threshold and began to dominate, and that is when the acceleration began. That is when the expansion stopped decelerating and started speeding up. Today, dark energy accounts for approximately 68% of the total energy content of the observable universe. Dark matter, the invisible gravitational scaffolding that holds galaxies together, accounts for roughly 27%. Ordinary matter, everything you have ever seen or touched or measured directly, every star, every planet, every atom of every element, accounts for approximately 5%. 5%. The universe is 95% things we cannot see and do not understand, and the dominant component, dark energy, is actively working to pull the observable universe apart, not violently, not suddenly, but steadily, persistently, without pause or variation, stretching the space between galaxies, accelerating the recession of everything beyond our local gravitational neighborhood, carrying distant objects toward and eventually past our cosmic event horizon. This is the consequence that matters most for our journey tonight. Because of dark energy, The observable universe is not merely a snapshot of the present, it is a diminishing window. Galaxies that are currently visible that we can study and photograph and analyze are moving away from us. Most of them are already receding faster than the speed of light in terms of their recession velocity due to expansion. The light they emitted long ago is still arriving, still crossing the shrinking distance between their past position and our present one. But the light they emit today and the light they will emit tomorrow and 1 billion years from now is already losing ground. That light will never arrive, and as time passes, more and more galaxies will cross our event horizon. Their most recent light will be the last we ever receive from them. After that, they will fade, not disappear suddenly. Fade, becoming dimmer and more red-shifted, their light stretched to longer and longer wavelengths, until eventually it falls below any threshold of detection and they vanish from our sky, not because they are gone, because they are too far. There is a number that captures the scale of this loss. Currently, the observable universe contains somewhere in the range of 2 trillion galaxies. 2 trillion distinct island universes, each containing hundreds of billions of stars. That number already staggers the imagination. But in the far future in the universe, that will exist trillions of years from now, after the acceleration has continued and the event horizon has swallowed galaxy after galaxy. The observable universe, of whatever observers might then exist, will contain far fewer galaxies. Perhaps only the few dozen members of our local group, the small cluster of galaxies of which the Milky Way is a member, all of them gravitationally bound tightly enough to resist the expansion. Everything else will be gone from the sky. Not destroyed, not dead, simply unreachable. Carried beyond the horizon by the relentless accelerating expansion of space, their light perpetually losing ground in the growing distance between us, never to arrive. Future observers, if they exist, will look up at a sky containing only a handful of nearby galaxies. They will have no evidence of the vast cosmic web we can see today. No evidence of the 2 trillion galaxies. No evidence of the large-scale structure. No way to measure the expansion of the universe the way we can, because the standard candles and the reference points will all be gone. No cosmic microwave background faintly detectable above the north, because it will have redshifted into wavelengths so long that no physical instrument could ever measure them. They will have no way of knowing that the universe was ever larger than what they can see. They will live in a cosmos that appears static, local, bounded, a sky of a few dozen galaxies surrounded by what appears to be an empty, featureless void. The true scale of the universe, the thing we are beginning to grasp right now in this narrow window of cosmic time, will be invisible to them, lost not to destruction but to distance, not erased but unreachable. And that means something about our moment. We exist at a time when the universe is still readable, when the ancient light of the Big Bang still reaches us from every direction, when 2 trillion galaxies still populate our sky, when the expansion is measurable, the structure is visible, the history is accessible. This will not always be true. The window is open now, the light is still arriving, the record is still available to read, and we are reading it. 0836. Claude responded. In 1964, 2 radio engineers at Bell Telephone Laboratories in New Jersey were trying to eliminate a problem. In 1964, 2 radio engineers at Bell Telephone Laboratories in New Jersey were trying to eliminate a problem. Their names were Arno Penzias and Robert Wilson, and they had been assigned to work with a large horn-shaped antenna originally built to communicate with early satellites. The antenna was extraordinarily sensitive, designed to pick up faint signals from space, and Penzias and Wilson were attempting to calibrate it with enough precision to make useful, astronomical measurements. But there was a problem they could not solve. There was noise, a persistent, low-level hiss in the detector that would not go away no matter what they did. They checked their equipment. They rechecked it. They ruled out interference from nearby New York City. They ruled out military radar. They ruled out interference from nuclear tests. They even found that pigeons had been nesting inside the antenna horn and had left what they carefully described in their notes as a white dielectric material coating the interior surfaces. They removed the pigeons. They cleaned the antenna. They did everything they could think of. The noise remained. It came from every direction equally. It did not vary with the time of day. It did not vary with the season. It did not correspond to any known source. It was simply there, uniform, persistent, apparently coming from the entire sky at once, from no particular direction, and from all directions simultaneously. What Penzias and Wilson had found without knowing it, without looking for it, while trying to solve what they assumed was an embarrassing equipment problem, was the oldest light in the universe. They had detected the cosmic microwave background. The signal they were hearing was not noise. It was the echo of the Big Bang itself, the relic radiation left over from the moment 380,000 years after the beginning, when the universe first became transparent and light was free to travel for the first time. That light had been traveling for nearly 14 billion years. It had crossed the entire observable universe. It had been stretched by the expansion of space from its original high-energy wavelengths into the microwave range, and it had arrived after that extraordinary journey in a horn-shaped antenna in New Jersey, where two engineers were trying to figure out why their equipment was not working properly. Penzias and Wilson received the Nobel Prize in Physics in 1978, but the discovery mattered far beyond the prize, because the cosmic microwave background is not merely an interesting feature of the universe, it is the single most important source of cosmological information we possess. It is a photograph of the universe at the moment it first became visible, and everything written in that photograph, every subtle variation in temperature, every pattern in the way the light is polarized, every statistical feature of its distribution across the sky, contains information about the state of the cosmos nearly 14 billion years ago. To understand why this light exists, and why it is the oldest we can ever receive, you need to understand what the universe was like before it was released. In the first moments after the Big Bang, the universe was not dark, it was not empty, it was not cold. It was a state of almost unimaginable density and temperature, a plasma so hot and so compressed that the fundamental particles of matter, protons and electrons, could not combine into atoms. Every time an electron approached a proton and began to form a hydrogen atom, a high-energy photon would immediately knock it loose. The universe was in a state of continuous violent thermal equilibrium. Matter and radiation were locked together, interacting constantly, exchanging energy, maintaining a temperature so extreme that the formation of even the simplest atom was impossible. In this state, the universe was opaque. Light, meaning photons, could not travel more than a tiny distance before colliding with a free electron and scattering in a new direction. The universe was in this sense like the interior of a star, or like an extraordinarily dense fog, or like the inside of a furnace. Photons were trapped, not in any container, but in the constant chaos of their interactions with matter. This continued for approximately 380,000 years. Then something changed. As the universe expanded, it cooled, the temperature dropped, and at a certain point, roughly 3000 Kelvin, something critical happened. The photons in the cosmic soup no longer had enough energy to ionize hydrogen atoms. Electrons began to settle into stable orbits around protons. Neutral atoms formed for the first time. And as neutral atoms formed, the universe became transparent almost instantly in cosmic terms, within a period of perhaps 100,000 years. Photons that had been trapped bouncing endlessly from electron to electron were suddenly free. They streamed outward in all directions, filling the universe with light for the first time. That light has been traveling ever since. It has never stopped. It has never been absorbed. It has only stretched as the universe expanded, growing cooler and cooler, shifting from the infrared to the microwave range, until today it fills all of space with a faint, cold glow at a temperature of approximately 2.7 Kelvin. 2.7 Kelvin. Approximately 2.7 degrees above absolute zero. The coldest temperature that physics permits is 0 Kelvin, and the cosmic microwave background sits just a fraction above that limit. It is cold in a way that has no ordinary analog. The coldest winter night you have ever experienced was vastly, enormously warmer than the background temperature of the universe. And yet, that faint cold glow carries within it the most detailed record of cosmic history we possess. When satellites like COBE launched in 1989 and WMAP launched in 2001, and most recently, Planck launched in 2009, mapped the cosmic microwave background with increasing precision, they revealed a sky covered in subtle variation. The background is not perfectly uniform. It is almost uniform, but across the entire sky there are temperature fluctuations of about 1 part in 100,000, regions that are slightly warmer, regions that are slightly cooler, patterns that are so faint they require instruments of extraordinary sensitivity to detect, but that contain encoded within them the entire future history of the universe. Those fluctuations are the seeds of structure, the slightly denser regions of the early universe. The places where matter was marginally more concentrated had slightly stronger gravitational fields. Over hundreds of millions of years, those regions pulled in surrounding matter. They grew. The slightly warmer and cooler patches in the microwave background correspond directly to those early density fluctuations, to the places where matter was beginning imperceptibly to clump, and those clumps became the first stars, the first galaxies, the first galaxy clusters, the vast cosmic web of filaments and voids that we see when we map the large-scale structure of the universe today. Everything you see when you look at a deep field image from a telescope, every galaxy, every cluster, every thread of the cosmic web, traces its origin to those tiny temperature fluctuations written in the oldest light we can see. But the microwave background tells us more than just where structure came from. It tells us the geometry of space. By measuring the angular size of the fluctuations, the apparent size of the hot and cold spots on the sky, cosmologists can determine whether space is flat open or closed. In a flat universe, those spots should appear at a certain characteristic size. In a closed universe, they would appear larger. In an open universe, smaller. What we measure matches the flat universe prediction with extraordinary precision. It tells us the composition of the universe. By analyzing the statistical patterns of the fluctuations, the way different size scales are represented in the temperature, map cosmologists can extract precise measurements of the amounts of ordinary matter, dark matter, and dark energy in the universe. The current best measurements give us approximately 5% ordinary matter, 27% dark matter, and 68% dark energy. Numbers consistent with every other measurement we have made using completely different methods. It tells us the age of the universe. The pattern of fluctuations depends on how sound waves propagated through the early plasma before the universe became transparent. By measuring those patterns precisely and comparing them to theoretical predictions, cosmologists can determine how long the universe has been expanding. The current best estimate is 13.8 billion years, with an uncertainty of less than 1%. All of this from a faint hiss in a radio antenna, from a signal that 2 engineers initially thought was a malfunction. But there is something even more important about the cosmic microwave background that we have not yet addressed. It represents a wall, not a physical wall, not a barrier you could approach and press your hand against, but an informational wall, a boundary in time beyond which we cannot see using light. Because before the universe became transparent, before the moment that produced the microwave background, light could not travel freely. Everything that happened in the first 380,000 years of cosmic history is hidden from us. Not hidden behind distance, hidden behind opacity. We cannot see the first stars forming because they formed after the background was released and are visible to us in principle, though very distant. We cannot see the epoch of reionization when the first stars and galaxies began to ionize the hydrogen gas around them, though it left subtle imprints on the background we can study indirectly. But we absolutely cannot see the plasma era. We cannot see the first minutes of nucleosynthesis when the first atomic nuclei formed. We cannot see the first seconds. Not with light. The universe in those early moments was opaque to photons. The record they carry begins at the surface of last scattering the moment the background was released and not before. Everything earlier is in the most literal sense invisible. This is one of the reasons physicists are so interested in gravitational waves. Ripples in the fabric of space-time are not affected by the opacity of the early universe the way photons are. Gravitational waves from the first fractions of a second after the Big Bang, if we could detect them, would pass through the plasma era without scattering, carrying information about a time we can never see with light. Instruments like LIGO and planned future observatories both on the ground and in space are working toward the sensitivity needed to detect this primordial gravitational wave background. If we succeed, we will have opened a new window, not into the observable universe as defined by light, but into an even deeper past, a time before the oldest light, a time that light itself cannot show us. But that window has not yet opened. For now, the cosmic microwave background remains the edge, the oldest message, the most ancient signal, the light that has been traveling longer than any other light in the observable universe, that has been stretched farther, cooled more, and yet still arrives, still fills the sky in every direction, still whispers to our instruments about a moment nearly 14 billion years in the past, when the universe first opened its eyes and let the light out. There is something profound in the fact that we can hear it, that the instruments we have built are sensitive enough to detect a signal so faint, so old, so thoroughly stretched by the expansion of space that it now lies in the microwave range far below any frequency visible to the human eye. That we have extracted from that signal a detailed map of the early cosmos and used that map to measure the age, shape, composition, and history of the universe with a precision that would have seemed like fantasy to the scientists of even a century ago. Penzias and Wilson heard something they did not understand. They assumed it was a problem to be solved, an obstacle to be removed. It turned out to be the most important signal ever detected, the universe announcing itself in the only way it could, with a whisper so ancient and so faint that it took the entirety of human ingenuity to recognize it for what it was, the echo of the beginning, still traveling, still arriving, still here. There is a problem with the cosmic microwave background that took cosmologists decades to fully appreciate. It is too uniform, not in the sense that uniformity is unexpected or unwelcome. The near-perfect smoothness of the ancient light is one of the most beautiful features of the observable universe. But when you examine it carefully, when you ask how that uniformity could have come to exist, you arrive at a conclusion that is deeply troubling within the framework of standard Big Bang cosmology. The problem is this: when we look at the microwave background in opposite directions of the sky, we are looking at regions of the early universe that were at the time the background was released, separated by distances so vast that no signal traveling at the speed of light could ever have crossed between them. Not in the 380,000 years that had elapsed since the beginning, not even close. The regions on opposite sides of our sky were, by the standard calculation, roughly 100 times farther apart than any causal connection could have bridged. And yet, they are the same temperature. Not approximately the same, not similar in the way that two distant places on Earth might have similar climates, the same to 1 part in 100,000, the same in a way that requires explanation. Because in physics, when two regions are at the same temperature, it means they have exchanged energy. They have been in thermal contact. They have had time to reach equilibrium. But if they were never in causal contact, if no signal could have ever passed between them, how did they reach the same temperature? This is called the horizon problem, and it is one of the most serious challenges the standard Big Bang model ever faced. There is a second problem equally serious, called the flatness problem. We have established that the universe appears geometrically flat. The measurements of the cosmic microwave background confirm this to extraordinary precision, but flatness in the context of general relativity is not a stable condition. It is an unstable equilibrium, like a pencil balanced perfectly on its tip. If the energy density of the universe in its earliest moments had been even slightly too high, space would have curved positively, and the universe would have collapsed long before stars could form. If it had been even slightly too low, space would have curved negatively, and the universe would have expanded so rapidly that matter could never have clumped into galaxies. The range of initial conditions that would produce a universe as flat as the one we observe is extraordinarily narrow. Cosmologists calculated that the energy density of the very early universe would have needed to match the critical value, the exact value required for flatness, to within 1 part in 10 to the 60th power. 1 part in 10 to the 60th. That is a 1 followed by 60 zeros in the denominator. A precision so extreme that it strains credibility to attribute it to coincidence or to some unspecified initial condition. Why would the universe begin in such a precisely tuned state? Both of these problems, the horizon problem and the flatness problem, pointed to the same conclusion. Something happened in the very early universe that we were not accounting for. something that connected distant regions, that smoothed out irregularities, that drove space toward flatness with overwhelming force. In 1980, a physicist named Alan Guth proposed an answer. Guth was 32 years old, working at Stanford, struggling with these same puzzles when he had what he later described as a spectacular realization. He had been thinking about phase transitions, the way matter changes state, as temperature drops, the way water freezes into ice, the way a magnet loses its alignment above a certain temperature and regains it below. In the very early universe, as the cosmos cooled from its initial extreme temperatures, it would have undergone similar phase transitions as the fundamental forces separated from one another. What if Guth reasoned one of those phase transitions had produced a brief period in which the universe was dominated by an enormous amount of potential energy, an energy stored not in matter or radiation but in the quantum field itself? And what if that energy had driven an exponential expansion of space, a doubling of size happening over and over and over again in an almost incomprehensibly short period of time? He called it inflation. The numbers that emerged from Guth's calculations were staggering. During the inflationary period, which is estimated to have lasted from approximately 10 to the negative 36 seconds to 10 to the negative 32 seconds after the Big Bang, the universe expanded by a factor of at least 10 to the 26th power. Some estimates place the expansion factor much higher, at 10 to the 50th or beyond. To grasp what this means, consider this. If you took a single proton, one of the tiny particles at the heart of every atom in your body, and inflated it by the same factor that the universe inflated during this period, it would become larger than the observable universe is today. Larger than the entire sphere of space containing 2 trillion galaxies, all the ancient light of the microwave background, all the structure and complexity of 14 billion years of cosmic evolution. That is how much space expanded in less than a billionth of a trillionth of a trillionth of a second. And this extraordinary expansion solved both problems simultaneously. The horizon problem dissolves because inflation tells us that the entire observable universe, all 93 billion light-years of it, inflated from a region so small that it was already in thermal equilibrium before inflation began. All the regions we see today, including those on opposite sides of the sky, were once in causal contact, once connected, once mixed, once the same temperature, for precisely the reason that temperature equilibration requires. They had time to exchange energy before inflation separated them. Inflation then stretched that small, uniform, balanced region into something vast. The uniformity was not a coincidence. It was a consequence of origin. Everything we see descended from the same tiny connected seed. The flatness problem dissolves in a similar way. Inflation drives the geometry of space toward flatness with extraordinary power. No matter what the initial curvature of the universe was, the violent expansion of inflation would have stretched any curve so severely that it became, for all practical purposes, flat. Think of the surface of a balloon as it inflates. From close up, the surface appears flat, regardless of the balloon's overall spherical shape. Now, imagine inflating that balloon to the size of the observable universe, while you remain at a fixed point on its surface. The local geometry would be indistinguishable from flat. That is what inflation does to space. It flattens it so thoroughly that even today, with our most sensitive measurements, we cannot detect any residual curvature. But inflation does something else, something that connects the largest scales in the universe to the smallest. During inflation, the universe was not perfectly smooth. Nothing in physics is perfectly smooth. At the quantum level, all fields fluctuate. There are always tiny random variations in energy density, microscopic ripples arising from the probabilistic nature of quantum mechanics. In ordinary circumstances, these fluctuations are negligibly small and disappear almost as quickly as they form. But during inflation, something extraordinary happened to those fluctuations. As space expanded, exponentially quantum fluctuations that existed on subatomic scales were stretched to cosmic scales before they could disappear. A fluctuation that began as a tiny random variation in the quantum field was inflated to a size larger than the observable universe in a fraction of a second. It was frozen into the fabric of space preserved by the expansion that outpaced any process that could have erased it. Those frozen fluctuations became the seeds of structure. The places in the early universe where matter was slightly denser, where the temperature was slightly higher, where the quantum field had fluctuated upward by an imperceptible amount during inflation, these became the regions where gravity was slightly stronger. Over hundreds of millions of years, that slight gravitational advantage compounded. More matter fell in, the density increased, stars formed, galaxies assembled, clusters grew, and the places where the field had fluctuated downward, where matter was slightly less dense, those became the great cosmic voids, the vast empty regions, hundreds of millions of light-years across, that we observe between the filaments of the cosmic web. Everything you see in the deep sky images, every galaxy, every cluster, every thread of structure in the large-scale universe traces its origin to a quantum fluctuation that lasted less than a Planck time during the first fraction of the Planck, first second of cosmic history. The largest structures in the observable universe are the fossilized imprints of the smallest possible events in the quantum world. That is one of the most astonishing facts in all of science. But inflation carries one more consequence, and it is the one that will occupy us most in the sections ahead. If inflation happened once, if the quantum field that drove it decayed and ended the inflationary period in our region of space, there is no reason to assume that it ended everywhere at the same time. In fact, in the most natural versions of inflationary theory, the field decays locally and randomly. In some regions it decays early, in others it decays later, and in some regions it may not have decayed at all. This is the picture that led to what cosmologists call eternal inflation. In eternal inflation, the universe is not a single inflating region that stopped and settled into a normal expanding cosmos. It is an endlessly growing structure in which inflation continues in most of the volume of space, while isolated regions stop inflating and evolve into pocket universes like our own. Our observable universe, our 46 billion light-year sphere, our 2 trillion galaxies, is one such pocket. One region where the inflationary field decayed, where the energy released in that decay reheated the universe and filled it with matter and radiation, where stars and galaxies and planets and perhaps observers eventually formed. But beyond our pocket, in the still inflating regions of the larger structure, space is expanding faster than light. New pockets are forming, new big bangs are occurring. New universes are evolving, each one causally disconnected from the others, each one separated by a growing ocean of inflationary space that no signal could ever cross. How many such pockets exist? The mathematics of eternal inflation suggests the answer is not merely large, it is unbounded. The inflationary structure produces new pockets endlessly, without stopping, without a final count, without a last universe. Whether this is truly infinite or merely larger than any number we can name, we cannot say. The mathematics permits infinity. Physics does not yet prohibit it. And within that possibility lies a cosmos so vast that our observable universe, our entire window, our entire scientific record, our entire history, is not even a rounding error in the total. It is a single bubble, in a structure that may have no end. This is not a comfortable conclusion. It is not supposed to be. The purpose of cosmology is not comfort, it is accuracy. And the most accurate picture we currently have of the universe beyond our horizon is this: space continues. It may continue forever. It was shaped by an event so violent and so brief that it defies any ordinary conception of time, and the universe we inhabit, the one we study, the one that feels so vast when we contemplate its 2 trillion galaxies and its 14 billion years of history, may be one of an uncountable number of such universes, each one as complex and as full as ours, each one forever beyond our reach. The first fraction of a second did not just create our universe, it may have created all of them. Science has a boundary, not a boundary of ambition, not a boundary of imagination, not a boundary imposed by the limitations of any particular instrument or the finite lifespans of the people who build them. A boundary that is more fundamental than any of those things. A boundary defined by a single requirement that has been at the heart of scientific inquiry since the method was first articulated. The requirement of testability. A scientific theory must make predictions that can in principle be checked against reality. It must say something about the world that could at least in principle turn out to be wrong. It must be falsifiable in the language of the philosopher Karl Popper. If a theory can accommodate any possible observation, if no conceivable experiment could contradict it, then it is not a scientific theory in the strictest sense. It may be a useful framework. It may be a beautiful piece of mathematics. It may even be true, but it cannot be confirmed or denied by the methods of science, and that places it in a different category. This boundary has served science extraordinarily well. It has kept the enterprise honest. It has forced theories to make specific checkable predictions rather than vague accommodating ones. It has provided a way to distinguish between ideas that explain the world and ideas that merely describe it. And now, in the early 21st century, cosmology has arrived at a place where that boundary becomes uncomfortably relevant. Because the ideas that follow most naturally from our best theories of the early universe, ideas like eternal inflation, ideas like the string theory, landscape ideas like the many worlds interpretation of quantum mechanics, all lead to the same conclusion. They lead to the existence of other universes, universes that are by the very structure of the theories that predict them permanently and fundamentally beyond any possible observation. Not just very far away, not just currently beyond the reach of our instruments, causally disconnected, separated by expanding space that no signal can cross, outside every possible light cone, beyond every conceivable horizon, unobservable in principle, forever. And this creates a genuine and unresolved tension at the frontier of physics. Let us look at each of the paths that lead here. The first path comes from eternal inflation, which we explored in the previous chapter. In eternal inflation, the inflationary field decays locally and randomly, producing pocket universes that are causally disconnected from one another. Our observable universe is one such pocket. Others exist in principle in enormous numbers, perhaps infinite numbers, but the space between pockets is inflating faster than light can cross it. No signal, no particle, no gravitational wave, nothing that physics currently describes can pass from one pocket to another. These other universes are not hidden behind a wall we might one day breach. They are separated from us by a process that is actively working against any possible connection, expanding the gap at rates that grow without limit. They are as unreachable as a point that exists outside of time itself. The second path comes from quantum mechanics, and it is stranger still. In the standard interpretation of quantum mechanics, when a quantum system is measured, the wave function that describes all its possible states collapses into a single outcome. An electron that could have been spin up or spin down is measured and found to be one or the other. The other possibilities simply cease to exist. But in 1957, a physicist named Hugh Everett proposed a different interpretation. Everett was a graduate student at Princeton, and he was troubled by the arbitrary nature of wave function collapse. Why should measurement be special? Why should the act of observation cause one possibility to become real and all others to vanish? The mathematics of quantum mechanics did not seem to require this. The equations described all possible outcomes evolving simultaneously. The collapse was something added to the theory, not something that followed from it. Everett proposed removing the collapse entirely. In his interpretation, which we now call the many worlds interpretation, measurement does not collapse the wave function. All outcomes occur, but they occur in separate, non-interacting branches of reality. When an electron is measured, the universe splits. In one branch, the electron is spin up. In another, it is spin down. Both branches are real. Both continue to evolve. Neither is aware of the other. This branching happens not just for deliberate measurements in physics laboratories. It happens for every quantum event everywhere in the universe, continuously at every scale. Every radioactive decay that could go one way or another. Every photon that could be absorbed or reflected. Every quantum fluctuation in the early universe. Each of these events produces branches. An uncountable, continuously growing number of parallel realities, each one as real as this one, each one containing observers who believe they inhabit the only universe. In the many worlds interpretation, there are no other universes in the sense of separate regions of space. There is one wave function, and it contains all possible histories. The parallel worlds are not spatially separated. They are separated in configuration space in the abstract mathematical space that describes all possible states of the universe simultaneously. You cannot travel to them. You cannot signal them. You cannot detect them through any physical means because by construction, the branches do not interact. And yet many physicists find this interpretation deeply compelling. Not because it is simpler in the ordinary sense. It obviously introduces an enormous number of additional branches. But because it is mathematically clean, it requires no arbitrary collapse. It requires no special role for measurement or observers. It requires only that you take the equations of quantum mechanics seriously and follow them wherever they lead. The third path comes from string theory, and it leads to the most elaborate vision of all. String theory is an attempt to unify all the fundamental forces of nature, including gravity, within a single mathematical framework. It replaces point particles with tiny, vibrating strings of energy, and it requires the existence of additional spatial dimensions beyond the three we experience. These extra dimensions are extremely small, curled up at scales far below anything we can currently probe, which is why we do not perceive them in everyday life. But the extra dimensions can be arranged in an enormous number of different ways. Different shapes, different sizes, different topological configurations, and each arrangement corresponds to a different set of physical laws, different values for the fundamental constants, different particle masses, different strengths of forces, different amounts of dark energy. The number of possible configurations that string theory permits is estimated to be something like 10 to the 500th power, a number so large that it exceeds the number of atoms in the observable universe by a margin so vast that no ordinary analogy can capture it. This collection of possible configurations is called the string theory landscape, and if eternal inflation is correct, then different regions of the inflating universe may have settled into different configurations as they stopped inflating. Different pocket universes may be described by different points on the string theory landscape, different physical laws, different constants, different possibilities for the emergence of structure, chemistry, and life. In some of those universes, the fundamental constants would be slightly different from ours. In many of them, those differences would be fatal to complexity. A slightly stronger, strong nuclear force and protons would fuse too readily for stable atoms to persist. A slightly weaker gravitational constant and matter would never clump into stars. A slightly larger cosmological constant, a slightly more powerful dark energy, and the universe would expand so rapidly that matter could never assemble into anything at all. Most configurations of the string theory landscape, if this picture is correct, would produce sterile universes without stars, without chemistry, without observers. But some configurations would be compatible with complexity, and those configurations would naturally contain observers to ask why the constants have the values they do. This is the anthropic principle in its cosmological form. The observation that we live in, a universe compatible with our existence, is not a coincidence and not a product of design. It is a selection effect. Out of an enormous number of universes with different properties, we inevitably find ourselves in one where the properties permit us to exist, not because we are special, not because the universe was made for us, but because in all the universes where the properties do not permit observers, there is no one to ask the question. This reasoning makes some physicists deeply uncomfortable. It feels less like an explanation and more like a retreat. If you can always say the constants have the values they do because if they did not, we would not be here to measure them, then you have not really explained anything. You have merely pointed out that observers observe observable universes. Others find the anthropic reasoning compelling precisely because it makes the fine-tuning of the constants less mysterious. If there are 10 to the 500th possible universes, then the fact that we live in one of the rare ones compatible with life is no more surprising than the fact that you live on a planet with liquid water and breathable air rather than on one of the many planets that have neither. The debate has not been resolved. It may not be resolvable. And that is the deeper issue. All three of these paths, eternal inflation, many worlds, the string theory landscape, lead to predictions that cannot be tested. Not currently, not with foreseeable technology. Not in many cases, in any possible future, regardless of technological progress. The other pockets in the inflating universe are beyond every horizon. The other branches of the quantum wave function do not interact with ours. The other points on the string theory landscape are as inaccessible as the inside of a black hole from outside its event horizon. If a theory predicts things that can never be observed or measured or falsified, is it science? The answer depends on what you believe science is for. If science is strictly an empirical enterprise, a method for making and testing predictions about observable reality, then theories that make only unobservable predictions are not science, they are philosophy. They are mathematics. They may be illuminating and beautiful and even correct, but they cannot be confirmed by the methods that give scientific theories their authority. But there is another view. If a theory makes testable predictions about the part of reality we can observe, and if those predictions are confirmed, then the theory gains credibility. And if that same theory also predicts unobservable things as a natural consequence of its structure, then those predictions carry some of the theory's credibility with them, even if they cannot be directly tested. Inflation makes testable predictions. It predicts the flatness of space, and we measure flatness. It predicts the nearly scale-invariant spectrum of fluctuations in the microwave background, and we measure exactly that spectrum. It predicts the overall uniformity of the background, and we observe that uniformity. Every testable prediction inflation makes has been confirmed. If that same inflation in its most natural versions also predicts eternal inflation and a multiverse of pocket universes, then those predictions carry some weight derived from the theory's success elsewhere. Not certainty, not confirmation, but something more than pure speculation. The same argument applies to many worlds and to string theory. The core of quantum mechanics is the most precisely tested theory in the history of science. If the many worlds interpretation is the most mathematically natural version of that theory, then it carries the theory's credibility even in its unobservable implications. This does not resolve the debate, but it reframes it. The question is not only whether the multiverse can be tested, it is whether our standards of evidence are adequate for theories whose full implications extend beyond the observable. That is not a question with a clean answer. It is one of the places where physics shades into philosophy, where the methods that have served us so well for 4 centuries begin to approach their own horizon. And perhaps that is appropriate. Perhaps it is fitting that a discipline devoted to understanding the universe should eventually arrive at questions that the universe itself places beyond complete resolution. We are not the first civilization to face the boundary of knowledge. We will not be the last. But we may be among the first to face a boundary that is not merely technological, not merely a matter of building better instruments or developing more powerful mathematics, but fundamental, structural, written into the laws of nature at a level that no future advance can circumvent. Beyond our horizon, the universe may be infinite. It may contain other universes. It may follow different laws in different regions. It may contain in some mathematical sense every possible reality, or it may not. We cannot know. And learning to hold that uncertainty without retreating from the question that may be the most important thing we can do. There is a question in cosmology that sounds almost too simple for a serious scientific discipline. What shape is the universe? Not what it looks like from the outside. There is no outside. Not what its contents are arranged into, not the shape of any galaxy or cluster or filament, but the shape of space itself, the geometry of the medium in which everything exists, the curvature of the fabric that inflation stretched, that matter warps, that expansion pulls, that dark energy drives apart. That question has a precise mathematical meaning, and pursuing its answer has led to some of the most important measurements in the history of cosmology. To understand what we mean by the shape of space, you need to set aside the ordinary notion of shape as something you can see from outside an object. You cannot step outside the universe and look at it the way you might look at a sphere or a saddle or a flat plane. You are always inside it. Whatever its shape is, you are embedded within it. And so the question of shape for a being living inside space becomes a question about how space behaves locally and how that local behavior accumulates over large distances. There is a branch of mathematics called differential geometry that deals precisely with this question. How do you determine the shape of a surface from measurements made entirely within that surface? without ever stepping outside it. The 19th century mathematician Carl Friedrich Gauss spent years thinking about this problem, and his student Bernhard Riemann extended the ideas into higher dimensions in ways that would not find their full physical application until Einstein used Riemannian geometry as the mathematical foundation of general relativity. The key concept is curvature. In a flat space, the familiar rules of Euclidean geometry hold exactly. The angles of a triangle add up to 180 degrees. Parallel lines remain parallel indefinitely. The ratio of a circle's circumference to its diameter is exactly pi. If you start at a point and travel in a perfectly straight line, you never return to your starting point. In a positively curved space like the surface of a sphere, these rules are violated in a specific way. The angles of a triangle add up to more than 180 degrees. Parallel lines converge. Draw two lines of longitude on a globe both perpendicular to the equator, and they are parallel at the equator, but meet at the poles. A circle's circumference is less than pi times its diameter. And if you travel in a perfectly straight line, you eventually return to your starting point. In a negatively curved space, like the surface of a saddle extended in all directions, the violations go the other way. The angles of a triangle add up to less than 180 degrees. Parallel lines diverge. A circle's circumference is more than pi times its diameter. Space expands outward faster than in the flat case. These are not merely abstract mathematical possibilities. General relativity tells us that the geometry of space is determined by its energy content, the total amount of energy in the universe, including matter, radiation, dark energy, and every other contribution determines whether space is flat, positively curved, or negatively curved. There is a specific value called the critical density, at which the energy content of the universe produces exactly flat space. If the actual density exceeds the critical density, space curves positively. If it falls below, space curves negatively. The ratio of the actual density to the critical density is given the symbol omega. If omega equals exactly 1, the universe is flat. If omega is greater than 1, it is positively curved and closed. If omega is less than 1, it is negatively curved and open. Measuring omega is therefore equivalent to measuring the shape of the universe. And the most powerful tool we have for making that measurement is the cosmic microwave background. Here is how it works. The tiny temperature fluctuations in the microwave background are not random noise. They have a characteristic angular size, a scale at which the fluctuations are most prominent, determined by the distance that sound waves could travel through the early universe before the background was released. That distance, called the sound horizon, is calculable from first principles. We know how fast sound traveled through the early plasma. We know how old the universe was when the background was released, so we can calculate how large those sound wave imprints should be in physical terms. What we can then measure is how large those imprints appear in the sky, their apparent angular size. And by comparing the apparent size to the known physical size, we can determine the geometry of the space through which the light traveled to reach us. If space is flat, the light traveled in straight lines, and the apparent size of the fluctuations matches what we expect from flat geometry. If space is positively curved, the light paths bend inward slightly over billions of years of travel, making the fluctuations appear larger than they would in flat space. If space is negatively curved, the paths bend outward, making the fluctuations appear smaller. This is in essence a cosmic measurement of the angle subtended by a known object at a known distance. The same principle you use when you hold a ruler at arm's length and measure its apparent size to estimate how far away it is, applied across the entire observable universe using the oldest light we can detect to determine the fundamental geometry of space. The result from the Planck satellite's most precise measurements, published in 2018, is that omega equals 1 to within approximately half of 1%. Space is flat, not probably flat, not effectively flat for practical purposes, flat within the precision of our best measurements, with uncertainties small enough that even a slight positive or negative curvature, if it exists, is below our current ability to detect. This result is consistent with inflation. As we discussed, the violent expansion of the inflationary period would drive the geometry of space toward flatness, regardless of whatever initial curvature existed. Inflation predicts a flat universe. We observe a flat universe. The agreement is one of the most significant confirmations of inflationary theory we have. But flatness raises a question that we touched on earlier and must now examine more carefully. A flat universe can be either infinite or finite, depending on its topology. Topology is a property of space that is distinct from its geometry. Geometry describes how space curves locally. Topology describes how it connects globally. A flat space in the geometric sense can still wrap back on itself in various ways, creating a universe that is finite in volume but has no boundary, no edge, no place where space ends. The simplest example is the torus. Imagine a two-dimensional flat surface that connects its left edge to its right edge and its top edge to its bottom edge, the way a video game screen wraps around. Locally, the surface is perfectly flat. The rules of Euclidean geometry hold, but globally the surface is finite. It has a fixed area, and if you travel far enough in one direction, you return to where you started. The three-dimensional analog of this, a three-torus, is a possible topology for our universe. Space could be flat locally, but connected globally, so that if you traveled far enough in any direction, you would eventually return to your starting point. The universe would be finite in volume, but have no edges, no boundaries, no place where space stops. If the universe has this kind of topology, there would be observable consequences. You would be able to see the same objects in multiple directions, as if you were inside a room lined with mirrors. The same galaxy would appear in opposite parts of the sky, or in multiple locations at slightly different positions. The cosmic microwave background would show repeating patterns, circles of matching temperature in opposite directions, where the same physical region was imprinting itself on the background from multiple angles. Searches for these signatures have been conducted with considerable care. Teams have looked for matched circles in the Planck data, for repeating patterns for any statistical anomaly that might suggest the universe wraps. So far, nothing convincing has been found. This does not mean the universe does not wrap. It means that if it wraps, it does so on scales larger than our observable sphere. The repeat length, the distance you would need to travel before returning to your starting point, must be larger than approximately 46 billion light-years. Otherwise, we would have detected the signature. So the topology is constrained but not determined. The universe could be infinite. It could be a torus with a very large repeat length. It could be any of a number of other topological configurations that are consistent with local flatness. We cannot yet distinguish between these possibilities with the data we have. What we can say is that if the universe is finite, it is much larger than what we can see. And if it is infinite, it is genuinely actually without boundary, or a space that extends forever in all directions, containing an infinite number of galaxies and stars and whatever else the physics of the cosmos permits. Now, consider what each of these possibilities means for the fate of the universe. In a closed universe, the positive curvature is associated with a density above the critical value. That excess density means there is enough gravitational attraction to eventually halt and reverse the expansion. The universe would reach a maximum size and then begin to contract, collapsing back on itself in what is sometimes called the Big Crunch, a mirror image of the Big Bang, but in reverse. All the matter and energy of the cosmos converging back toward a single point of infinite density. Whether a Big Crunch would produce a new Big Bang, whether it would bounce, whether any information from the collapsed universe could persist into whatever came after, these are questions we cannot currently answer. But the closed universe has a finite future as well as a finite past, a beginning and an end, with a vast arc of expansion and contraction between them. In an open universe, the negative curvature is associated with a density below the critical value. Gravity is not strong enough to halt the expansion, which continues forever. Distances grow without limit. Stars exhaust their fuel and die. Black holes eventually evaporate through Hawking radiation. The universe approaches a state of maximum entropy, a cold, dark, diffuse equilibrium, in which nothing more can happen. This is sometimes called the heat death of the universe, or the Big Freeze. In a flat universe, The geometry sits precisely at the boundary between these two fates. Mathematically, a perfectly flat universe with no dark energy would expand forever, but at a rate that asymptotically approaches zero. It would never collapse, but it would never truly escape the gravitational pull of its own contents either. It would slow and slow and slow, approaching stillness without ever reaching it. But we do not live in a flat universe without dark energy. We live in a flat universe with dark energy, and dark energy changes everything about the long-term fate of the cosmos. Because dark energy does not dilute as space expands, it does not weaken. In the current model, it maintains a constant density, regardless of the volume of space, which means its influence grows relative to matter and radiation as the universe expands and those components thin out. Dark energy is already the dominant force shaping the large-scale behavior of the universe, and it will become more dominant over time, not less. The consequence is that the universe will expand forever, not slowing towards zero but accelerating. Distances between unbound structures will increase without limit. The event horizon will swallow more and more of the observable universe. Galaxies will fade from view. The sky will empty. The cosmos will grow cold and dark and vast beyond any current conception of vastness. Not because of its shape in the geometric sense. The universe will remain flat throughout this evolution, but because of the energy that fills it, the invisible pressure that pushes space apart, and will continue to do so for as long as the current model holds. The shape of the universe is flat. The fate of the universe is expansion without end. And somewhere in the space between those two facts, in the gap between the geometry we can measure and the future we can project, lies everything we do not yet know. Every question that remains open, every answer that the observable universe has not yet provided and may never provide. The shape is flat, the future is open, and the horizon in every direction is receding. Picture the night sky 10 trillion years from now. Not the sky as it appears tonight, dense with the light of hundreds of billions of stars in our galaxy alone, framed by the faint smudges of neighboring galaxies visible to the naked eye, surrounded by the invisible presence of 2 trillion more galaxies filling the observable universe in every direction. Not that sky, a different sky, a quieter sky, a sky that has been slowly, steadily, irreversibly emptied by the one force in the universe that operates without pause, without relent, without any possibility of negotiation. The expansion of space. In that distant future, the Milky Way will still exist, merged by then with the Andromeda Galaxy and several smaller companions into a single large elliptical structure that astronomers today sometimes call Milkomeda. The stars of that merged galaxy will still burn, though many of the smaller, longer-lived ones will be the predominant survivors. The massive, brilliant stars long since exhausted and dead, there will still be planets. There may still be, for all we can project, something capable of looking up. But what that something sees will bear almost no resemblance to what we see tonight. Every galaxy beyond our local group, every one of the roughly 50 or so gravitationally bound neighbors that make up our immediate cosmic neighborhood will be gone from the sky. Not destroyed, not dead, simply beyond the horizon. Carried past the cosmic event horizon by the relentless acceleration of dark energy, their light perpetually losing ground in the growing gap between us and them. Their last photons fading to wavelengths so long that no physical instrument built from ordinary matter could detect them. The Virgo cluster, the nearest large galaxy cluster, containing more than 1,000 galaxies, including the giant elliptical Messier, 87 at its heart, will be gone. The Coma cluster, several hundred million light-years away, will be gone. The great filaments of the cosmic web, the vast threads of matter, connecting clusters across hundreds of millions of light-years, will be gone. The deep sky, the breathtaking field of galaxies that fills every patch of darkness in a long-exposure image from any of our great telescopes, will be gone. The sky will contain a single galaxy, the merged remnant of our local group, surrounded by darkness. Not empty darkness. The space will still be there, the matter will still be there, the physics will still be operating according to the same laws. But from the perspective of any observer within that future galaxy, the universe will appear to be exactly what it is not: small, local, bounded, a single island of stars in an otherwise featureless void. And here is the part that settles most heavily, that carries the most weight when you truly let it in. Those future observers, whatever they are, will have no way of knowing otherwise. The cosmic microwave background, the ancient light that currently fills every point in space with its faint 2.7 Kelvin glow, the light that carries within it the entire history of the universe from its first 380,000 years will by then have redshifted into wavelengths so extraordinarily long that they lie far beyond the sensitivity of any detector built from atoms. The signal will effectively have vanished, not because it stopped traveling, but because the universe will have expanded it into silence. The large-scale structure of the cosmos, the filaments and voids and clusters that we use today to measure the expansion, to trace the history of dark energy, to confirm the predictions of inflation, will all be beyond the horizon. The standard candles we use to measure cosmic distances, the type Ia supernovae that revealed the acceleration in 1998, will mostly be gone from view. The reference points that allow us to construct a picture of the universe as it truly is will have been systematically removed one by the very process we are trying to study. Those future observers will build their cosmology from what remains, and what remains will be a single galaxy in an apparently empty universe. They may conclude reasonably and with complete internal consistency that the universe is small, that it always was small, that there was never anything beyond their horizon because there is no evidence of anything beyond their horizon. They will have no fossil record of the wider cosmos, no ancient light from a hotter, denser era, no tracery of structure across a sky that once held 2 trillion galaxies. The evidence will not have been erased. It will have been carried away. Every piece of information that we currently use to reconstruct the history of the cosmos, to confirm the Big Bang, to measure the age and composition and geometry of the universe, depends on signals that are still arriving. Depends on light that left its sources in the distant past and is only now completing its journey to our instruments. That light is still here. That information is still available, but it will not always be. We live in a privileged moment. Not privileged in the sense of being chosen or special or intended. Privileged in the purely physical sense of occupying a position in time when the universe is still readable, when its history is still written in accessible light, when the signals from its earliest moments are still arriving and have not yet faded below the threshold of detection, when the large-scale structure is still visible in its full complexity, when the expansion is still measurable against the backdrop of a sky full of reference points. This window opened roughly 14 billion years ago when the universe became transparent and light was first free to travel. It will close gradually and irreversibly as dark energy continues its work, and the observable universe empties of the distant galaxies whose light carries the record of cosmic history. We are somewhere in the middle of that window, perhaps past the middle. The acceleration has been underway for roughly 5 billion years, and its effects are already being felt in the gradual recession of distant galaxies toward and beyond our event horizon. The window is open now. It will not always be. That fact gives the work of cosmology an urgency that is easy to overlook when you are focused on the technical details of data analysis and theoretical modeling. Every observation is a race not against a deadline imposed by funding or politics or the limitations of any particular instrument, but against the fundamental physics of an expanding universe. Every galaxy catalogued, every measurement of the microwave background refined, every supernova studied, every piece of the cosmic puzzle assembled is a record made while the record is still available to make. The maps we draw now, the models we build now, the understanding we reach now, these may be the only complete account of the universe that will ever be possible. Not because future civilizations will lack the intelligence or the dedication to study cosmology, but because the universe will have hidden its own history from them carrying the evidence past the horizon on the silent tide of accelerating expansion. And yet, there is something in this picture that moves in the opposite direction from despair. Something that, if you sit with it long enough, begins to feel like the opposite of smallness. Consider what we have done. We are a species that evolved on a small rocky planet, orbiting an unremarkable star in the outer region of a spiral galaxy that is one of 2 trillion. We have been doing science in the modern sense for less than 500 years. We have been doing physics with mathematical precision for less than 400. We have had access to space-based telescopes for less than 60. We have known about the existence of other galaxies for less than a century. We have known about the acceleration of the universe's expansion for less than 30 years. In that extraordinarily brief period measured against the 14 billion-year history of the cosmos, we have determined the age of the universe to within 1%. We have mapped the cosmic microwave background with enough precision to extract the composition, geometry, and expansion history of the observable universe. We have detected gravitational waves, ripples in the fabric of space-time itself, produced by the collision of black holes more than 1 billion light-years away. We have imaged the shadow of a black hole at the center of a galaxy, 55 million light-years distant. We have identified the seeds of structure in the oldest light we can observe and traced those seeds forward through 14 billion years to the galaxies and filaments we see today. We have done all of this from inside a single bubble of visibility, using instruments built over a few decades by a species that has existed for a few 100,000 years on a planet that formed 4.5 billion years ago. We have measured the universe. Not all of it, not even most of it, perhaps not even a measurable fraction of the whole, but we have measured what we can reach. We have pushed the methods of rational inquiry to the very edge of the observable, and in some cases beyond it, into the territory of careful, rigorous inference. We have built a picture of the cosmos that is internally consistent, that makes precise predictions, that has been confirmed by observation after observation after observation conducted by different people using different methods in different places at different times. That is not a small thing. That is perhaps the most extraordinary thing a mind has ever done, because a mind is not supposed to be able to do that. A mind is a small, temporary, improbable arrangement of matter that arose by the slow processes of evolution on the surface of a planet. It is built to navigate the immediate environment to find food, to avoid predators, to communicate with others of its kind. It is not built to comprehend the curvature of space-time, or the geometry of an inflationary universe, or the physics of a cosmic microwave background. It has no evolutionary reason to understand any of those things, and yet it does, partially, imperfectly, provisionally, with errors and revisions and ongoing debate, but it does. You can hold in your mind right now the knowledge that the universe began approximately 13.8 billion years ago in a state of extraordinary density and temperature, that it expanded and cooled, that a fraction of a second into its existence it underwent an inflationary expansion that stretched quantum fluctuations to cosmic scales and set the seeds of all subsequent structure. That 380,000 years later, it became transparent and released the light we now call the cosmic microwave background. That over the following hundreds of millions of years, the first stars ignited, burning through their nuclear fuel and seeding the universe with the heavier elements from which planets and life are made. That galaxies assembled, evolved, merged. That approximately 5 billion years ago, the expansion of the universe began to accelerate, driven by a form of energy we cannot directly detect and do not fully understand. That today, the observable universe spans 93 billion light-years and contains 2 trillion galaxies, each one a collection of hundreds of billions of stars, most of them orbited by planets. Some of those planets, perhaps, harboring the same improbable arrangement of matter and chemistry that allows a mind to sit quietly in a darkened room and contemplate the whole of what exists. You can hold all of that in a universe that is mostly hydrogen and helium and vacuum and dark energy and the long silence between galaxies. You can hold that. That is what lies beyond the last light. Not darkness, not emptiness, not absence, more universe, more space expanding away faster than any signal can follow. More galaxies inaccessible, not because they do not exist, but because the distance between us is growing at a rate that no physics currently known could overcome. More history, more structure, more of the quiet and enormous complexity that characterizes the cosmos at every scale we have ever been able to examine. And perhaps in some of those unreachable regions, more minds, more improbable arrangements of matter that have found themselves looking outward from their own small planets toward their own versions of the same horizon, asking their own versions of the same question. What lies out there past the edge of what the light has shown us? The answer is the same from every point in the cosmos, from every observer, in every pocket universe, in every galaxy, on every planet, where something has ever managed to look up and wonder, more, always more. And between us and that more stretching in every direction across distances that dwarf every scale of ordinary experience, the light is still traveling. Ancient light from the first transparent moment of the universe, still crossing the expanding space between its origin and us, still carrying its record of the earliest cosmos, still arriving after a journey of nearly 14 billion years. It reaches you now, right now, in this room, in this moment. The universe is speaking in the only language it has, the language of light traveling across time, and for this brief, extraordinary, unrepeatable window in the history of the cosmos, we are here to receive it. The horizon is out there, receding in every direction, carrying the rest of the universe beyond our reach. And here inside it, in the small warm space defined by all the light that has managed to arrive, something looks out and wonders. And that in a cosmos this large and this old and this indifferent to the brief arrangements of matter that occasionally manage to comprehend it is the most astonishing thing of all.